the Hilbert transform. So we're going to start with this function. So suppose we have a function which is, let's take it to be C infinity of compact support on R. Then we're going to define the following thing. We're going to define h of f of x to be the integral of f of x minus t dt over t, like this, over the entire real line. Well, we'd like to do this, but this a priori makes no sense because this is not an integrable kernel, so it's not clear to us that this even makes any sense by itself. So we are going to define it in the principal value sense. I mean, we've already seen this in the Burning transform, that we could make sense of the integral away from a particular ball, outside a particular ball that goes to 0. So we're going to define it like this. So take away the ball of radius epsilon around 0. And it still doesn't make sense necessarily unless this limit exists. Yeah? So you need to show this limit exists. This limit exists. And in this case, for this smooth function, everywhere. So how do we do this? So to see this, first note that since f has got compact support, there exists some r which is bigger than 0, which depends both on x and on f. Such that the integral of take away the ball of radius epsilon around 0, f of x minus t over t dt is just going to be the integral from minus r to r, take away the ball of radius epsilon around 0, like this, and f of x minus t over t dt. Because f has got compact support, so if we take this r large enough, then ultimately f is just 0, so there must exist some r such that this is true. Yeah? And then this will be true for all small enough epsilon, right? Because it just depends on the fact that we are outside of this r, then this thing is just vanishing. Yeah? So all small epsilon. Okay, so once we do this, then let's do the following. So let's call this thing star. And star, we can also write as the integral from minus r to r. Take away this ball of radius epsilon around 0, and let's put in this f of x minus t over t minus f of x over t dt. And we can do this because this thing we add is just going to be 0, right? So f of x, we can pull it outside the integral, and then we're just integrating something on this thing here. So it's minus r to minus epsilon, and then it's epsilon to r, right? So if we integrate this, oops, I could have just written it as a ball of radius r. Yeah, let's do that. So if we integrate ball of radius r around 0, take away the ball of radius epsilon around 0 of 1 over t. since we're avoiding 0, this thing does make sense, and just by symmetry, this is just 0. Yeah? So we can put this expression inside this, and then nothing goes wrong. Yeah? Everybody agree? So let's write this guy as the integral of minus r to r, take the polar radius epsilon around 0, and let's put the common denominator f of t like this. Oops, f of x, sorry. Over t dt, yeah? And we can further write this guy as the integral of minus r to r of the characteristic function of the set of x such that, or set of t, actually let's give ourselves a new variable, set of y such that mod y is bigger than epsilon, like this, t, and then this thing, f of x minus t minus f of x over t dt. We could do that. Yeah, that's exactly the same integral. Yeah? But let's look at this thing. So this thing is this difference quotient, right? And what we have is a C infinity function. It's enough actually for it to be C1, which has got compact support. So it's actually Lipschitz, right? So this quotient here will be bounded. This will be bounded, right? So by the mean value property, this thing is bounded by f prime for some f prime between x minus t and x, yeah? And since we are C1, C infinity, whatever, f prime is a bounded thing itself. So this thing inside the brackets is just uniformly bounded. Yeah? Cool. And this thing is just the characteristic function of everything outside of the border radius epsilon. Yeah? So this thing here we can think of as a sequence of functions that depend on epsilon, right? We could call this thing g of epsilon of t if we wanted to. Yeah? And then this thing would be a sequence of functions dependent on epsilon that is uniformly bounded. Yeah? Yeah? So in particular, since we're dealing with this finite set minus r to r, we have that we can apply the dominated convergence theorem. So by dominated, we can pass to the limit through this integral. So the limit as epsilon tends to 0 of the integral from minus r to r of this g epsilon of t dt will actually be this thing. So some of you have done real analysis and you've seen the dominated convergence theorem, but maybe not everybody. All right, okay, cool. So I guess everybody's seen the dominated convergence theorem. Yeah? All right, so then this is just an application of dominated convergence theorem because this is a sequence of functions that is uniformly integrable, yeah, because they're uniformly bounded on a finite set, on a bounded set. Yeah? So we can indeed just pass through the integral through the limit like this. Yeah? And if we look at this thing, then this thing does indeed have a limit as epsilon goes down to 0, and that limit is just this function here. Right? It's just this function here, excluding the value t equals 0. Yeah? Cool. So that means that this limit actually does exist because this function does have a limit, right? So this is just the integral from minus r to r of excluding the value 0 of f of x minus t minus f of x over t dt. And that is something that makes sense, right? So the limit does indeed exist, and this thing is a well-defined thing for every single x. Yeah? Are you with me, and do you agree? Yeah? Everybody happy? Cool. All right. So it defined. We've done this for C infinity functions of compact support. As you can see, C1 would be enough. In fact, compact support is not strictly necessary. If the function decayed fast enough, then we wouldn't have to worry about this kind of stuff. The fact that it was non-zero as we went to infinity would not be a problem if it decayed fast enough. So there's something called a Schwartz class where you can define this first. Yeah. But let's not go into that. Let's just stick with this for the time being. And we are happy that we have something that makes sense. It's also easy to see that this is a linear operator, right? If we apply this to f1, f2, that's the same as h of f1 plus h of f2. Yeah? And it's also easy to see that if we put lambda times f, then we just pull it out. Yeah? So this is a nice linear operator, yeah, on the space of this moment, C infinity functions of compact support. Yeah? Cool. All right, I'm going to raise the board, and then we'll talk about some more properties that it has. Okay, so the Hilbert transform, so I'm just going to call it the H transform from now on. Commutes with dilations and translations. So what I mean by this is that given some smooth function, compact support in R, and some x0 belong to real numbers, let's define f of x0 of x to be f of x plus x0. So we're just translating it by x0. Yeah? Then let's see what happens when we act with the Hilbert transform on this translated function. So f of x0, like this. X, what is that? That's the integral of f of x0 of x minus t over t dt, integral over r. Okay, so I'm going to write principal value now, where principal value means that we're taking this limit as epsilon goes to 0 of the integral of the real numbers take away a ball of radius epsilon around 0. Okay, so maybe I put this somewhere else. So principal value of an integral over r, whatever dt, is the limit as epsilon tends to 0 of take away the ball of radius epsilon around 0, whatever it is, like this. Okay, so in the principal value sense, we have this thing, and then it should put in what this is. So this is principal value integral over r of f of x0 plus x minus t over t. Yeah, but then that is exactly the same as the Hilbert transform on f applied to this point x0, like this. Yeah? So that is like taking the Hilbert transform as a function and then translating it in exactly the same way we've done it, like this. Okay? So this behaves well with translations. We can translate the inner function, and that's the same as translating h of this function itself. Yeah? Cool. And same thing is true of dilation. So given some lambda bigger than 0, okay, let's define f of lambda of x to be f of lambda times x, like this. And then let's see what happens when you do the Hilbert transform of this dilation. This is principal value of the integral of f of lambda x minus t over t dt. This is a little bit more subtle, so this is principal value of the integral of f of, using this definition here, lambda of x minus lambda of t over t, like this, dt. Yeah? And let us define, I'm going to separate my lines here. And then let us define, or let us take a new variable. So let s be lambda times t, right? So ds equals lambda times dt, like this, and t is equal to s over lambda, like this. Yeah. So let's write this in terms of our s. So this is, so actually let us now, just to be very careful, let us write down what principal value means. So this is the limit as epsilon tends to 0 of the integral of the real numbers take away ball of radius epsilon around 0. So when we are in variable t, so if t is not inside the ball of radius epsilon, that's the same as absolute value of t is bigger than epsilon, and then this is the same as s over lambda is bigger than epsilon. Which is the same as mod s is bigger than epsilon times lambda. Okay, so when we do all of this stuff now in our new variable, this is the limit as epsilon tends to 0, the integral, and now it's r, take away the ball of lambda epsilon around 0, and here we're going to have f of lambda x minus s. T is s over lambda, so this is s, but then we're going to lambda like this, and dt is ds over lambda, so then it's ds over lambda, and these lambdas cancel, right? These lambdas cancel, and then as we take epsilon going down to 0, lambda is some positive number, right? So the limit of this thing is going to be exactly the same thing as the limit of r take away the ball of radius delta as delta goes to 0. We could just define delta to be lambda times epsilon. Yeah? See what I mean? So my claim is that this is exactly the same as the principal value of the integral of f of lambda of x minus s over s ds. Yeah? But this is just the Hilbert transform of f evaluated at the point lambda x. Yeah? So this is the same as doing the Hilbert transform and then dilating it by lambda like this. Yeah? Is everybody happy? Yeah? So this guy behaves very nicely with respect to dilations and translations. And this is quite a very, like I think, a unique property of the Hilbert transform. All right, cool. So we are going to need an inequality which is kind of non-trivial, and I'm thinking I should just erase the board. And it's spelled like this: P. I don't know how to say this name, but this is the name. And it is this. So, given f, we're going to take it to infinity, complex support in R, and for any x belonging to R, we're going to take the following thing. We're going to take 1 over 2 pi I, the integral of f of y of y minus x plus I times epsilon, like this, dy. And that's going to be equal to f of x plus I times the Hilbert transform of f of x over 2. That is our formula that we'll need shortly. So let's look at what we are doing. We are taking the real line, we're taking some point x on the real line, and we're taking this point x plus I times epsilon. Yeah? And we are considering this singular type integral. Okay? But it's not quite singular because this is integrating over y on the real line, So this thing is not actually equal to 0, right? This is a complex number, right? So we're integrating this thing times this thing, or this thing divided by this thing. Yeah? And implicit in this is the fact that this integral will converge and be equal to this actual thing right here. Yeah? So this is just a calculation at this point, and I don't have much motivation to give you for it. So what we're essentially saying is that this thing, which is a complex integral, it's integrating with respect to y, but this is a complex number integrating, which changes with respect to y, ends up being this thing here, which is, so if we're dividing it by 2 pi I, so this overall complex number ends up having this is the real part and the imaginary part is the Hilbert transform. Okay? And yeah, let's just do this calculation, and then the next class you'll see why this is useful. All right, so let's get to work on this. So proof. How should we write this? So let's minus epsilon goes to 0. Okay, yeah, because there's no epsilon on the right hand side. Okay, so let's look at this. Why is this true? So this is f of x over 2, and then I over 2, the Hilbert transform. And what's the Hilbert transform? It's the integral in the principal value sense. Of f of x minus t over t, it's 1 over pi. Hopefully I was putting the 1 over pi in the definition of the Hilbert transform, but I fear I wasn't. Okay, might have to superimpose this constant 1 over pi after the fact. Okay, so this is the definition of the Hilbert transform. So for this formula to be true, then let us put all the integrals on the same side and incorporate limit as epsilon goes to 0. So we know what this means. This is f of x over 2, and then plus I over 2. Let's put it like this, 2 pi. And then the limit as epsilon goes to 0 of the real numbers, take away the ball of radius epsilon around 0, f of x minus t over t dt. Right? So let's put that stuff on the other side and incorporate the epsilon. So our claim, so let's call this thing star. So star is equivalent to the following thing, that the limit as epsilon goes to 0, shall we pull out the 1 over 2 pi I? Yeah, let's pull out the 1 over 2 pi I straight away. And then it's the limit as epsilon goes to 0. So we can write this as like minus 1 over 2 pi I. So if we put it on the other side, then we're going to get a plus. So then this will be the integral of f of y over y minus x plus I epsilon. And now we're going to have plus, we might as well do the integral in y because why not? Because we have y here. So then we're going to have x minus y over y. But we need to avoid the ball of radius epsilon, so characteristic function, set of s such that mod s is bigger than epsilon, like this, y dy. Yeah? So we pull that on the other side, and the claim is therefore that this is equal to f of x over 2. Yeah? Everybody happy? Cool. All right, so let us look at this guy right here. Oops, everything is making sense. So let's change this guy around so it's in the similar form of this thing. Yeah, actually, let's make our life simpler just by assuming that x is equal to 0. So if this is true for x equals 0, then it's true for general x by simple stuff. So assume that x is equal to 0, and then this becomes 1 over 2 pi I, the limit as epsilon goes to 0 of the integral of f of y over y minus I times epsilon plus f of minus y. I don't like the minus y, so I'm going to change that around in a second. Characteristic function of s dy. So in this part of the integral, I want to change minus y to y. So let's call y tilde minus y. So then dy tilde equals minus dy. And then this thing will remain the same, right? And so we'll have y tilde, we'll have minus y tilde, but we'll also get a minus from replacing the y by minus y. Yeah? So let's write it in. So then this thing will become y tilde, this will be minus y tilde, and this will be minus dy tilde. Yeah? And then the minuses cancel. So what that means is that I can actually write this as 1 over 2 pi I. The limit as epsilon goes to 0. And this thing is just going to remain the same, symmetrical condition. So what I'm going to get is f of y, 1 over y minus I epsilon. And then from this, the minuses will cancel. So then this will just be plus 1 over y dy. 1 over y dy, excluding the ball of radius epsilon. And the characteristic function of the set of S, such that not S is bigger than epsilon times y itself, dy, like this. Does everybody agree? Everybody with me here? Yeah? Cool. So, now what I'm going to do is I'm going to make a change of variables, and I'm going to let w be such that epsilon times w is equal to y. In other words, w equals y over epsilon, dw equals dy over epsilon. And I'm going to rewrite everything in terms of w. So 2 pi I, limit is epsilon goes to 0. And then we're going to have f of epsilon w. We're going to have 1 over epsilon w minus I times epsilon. And then we're going to have plus 1 over epsilon w. And then this is the characteristic function of everything bigger than epsilon. And now we have epsilon w. And the dy is now epsilon times dw, like this. Yeah? And then we see that these epsilons in the denominator will cancel with this epsilon right here. Yeah? So then this thing is just going to become 1 over 2 pi I, the integral, the limit as epsilon goes to 0 of f of epsilon w, I'm running out of space here, 1 over epsilon w minus, no, the epsilons have vanished. 1 over w minus I plus 1 over w. And if mod s is bigger than epsilon, since w, start again. So if epsilon w is being hit, if we were getting a 1 out of this set here, that means that w will have to have absolute value bigger than 1. Yeah? So then we can rewrite this thing as the characteristic function of the set of s such that absolute value of s is bigger than 1 times w, like this. dw. Yeah? Cool. So what's our claim? Our claim is that this whole stuff tends to f of x over 2. And x we've taken to be 0, so that's like f of 0 over 2, right? So if we look at this guy right here, as epsilon goes down to 0 by continuity, this is tending towards just f of 0. Yeah? So our claim will be proved if we get that this integral tends to pi times I. So claim that the integral, well, not tends to because we've taken the epsilon out, the integral of 1 over w minus I plus 1 over w, characteristic function of the set of s, such that mod s is bigger than 1, times w dw is equal to pi times I. And if we could show that, then we are in very good shape, because this thing again is tending down towards this particular fixed value f of 0. Yeah? This integral is, if it actually is equal to pi times I, then in the limit as epsilon goes to 0, this will just be f of 0 times pi times I divided by 2 pi I, and it'll give us exactly f of 0 over 2. Yeah? All right, look at this calculation here. What simplification do we see here? What simplification do we see here? So everything, whenever I'm not writing, everything is integral over the entire real line. Okay, so back to this. What simplifications do we see here? Yeah, second term will just go away, just by symmetry. Yeah, just by symmetry. Yeah. So enough. To show that the integral of 1 over w minus I dw is equal to pi I. Yeah? Are you all with me that that's enough? That's all we need to show. Thumbs up if yes, thumbs down if no. All right, cool. So I'm going to raise the board, and then that'll be our mission. And in the meantime, while I'm erasing, think about how we can show this. And what is the nature of this? This is integrating a holomorphic function, right? It's integrating a holomorphic function over the entire real line. Yeah? Yeah? And think about how we might be able to do that. We know a lot about integrating holomorphic functions. Well, it's holomorphic, but it has a singularity, so it's a meromorphic function. We know a lot about integrating meromorphic functions under some circumstances, right? But here we have an integral over a line rather than a closed curve. Yeah? But think what we can do. Okay, so want to show, so claim is that the integral of 1 over w minus I, the w of the entire real line is equal to pi times I. So suggestions, how could we do this? But residue theorem is when we have a closed curve containing the singularity. So how? Yeah. So normally, well, I mean, many times we've done real integrals by considering like a semicircle like this, yeah? And then if the decay on this guy is of order 2 or more, then this thing vanishes, right? Because it's something of length times the radius. And if this thing was like 1 over r squared, then we would have a chance to actually show it vanishes, yeah? See what I mean? But we don't have that here because this thing is of order 1 over the radius, and we're integrating something of length times the radius. So the integral around the semicircle here isn't going to vanish. Yeah? Are you people with me? Yeah? I might have time, a little bit over time. Okay, so I want to finish this calculation. Some of you have to leave, just leave whenever you want. So there's no way to make this semicircle thing vanish. Just the order of decay of this is the wrong order. It's actually part of the integral. If we do a semicircle like this, the semicircle will be part of the answer. Yeah? So the only thing to be done is to actually calculate what contribution the semicircle is giving. Yeah? Yeah? And to make it a little bit easier, we're not going to do a semicircle centered on 0. We're going to make a semicircle centered on I. Because when we do a semicircle centered on I, then actually calculating what this thing is will be easier. Yeah? Do you see what I mean? So this is what we're going to do. So if we put a circle of radius r on I, then it's going to, sure enough, cross the real axis, but it's not going to cross. It's not going to cross at whatever, at 0 and pi. It's going to cross at things that are a little bit different. Yeah. A little bit more, but it'll tend to more and more as we tends towards larger and larger radius. It'll be more and more like we took the circle centered on I. So these things won't be too big a problem for us. But let us define our contour. So this is of radius capital R around I, and then it intersects at these points like this, and let's call this A of R, and let's call this B of R. Yeah? And as r tends to infinity, A of r and B of r are going to tend to infinity, and then we're going to take the limit as our capital R tends to infinity. Yeah? So let's call this contour gamma of r. Yeah? So by the residue theorem, I should start with the proof. By residue formula, if we do this integral over gamma of r of this holomorphic function, w minus I, or this meromorphic function, dw, this now means a complex integral, this thing will be equal to the residue evaluated at I, right? Yeah? So what will the residue evaluated at I of this holomorphic function be? So let f of w be 1 over w minus I. Then this is 2 pi I, and the residue of f at I. Yeah? And the residue of f at I. What kind of pole do we have here? Simple pole, right? So we can calculate the residue. What's the formula? Yep, the limit is, we're doing this with w, but w tends to I of w minus I of f of w, like this. Yeah? And then what's this? This is the limit as w tends to I of w minus I over w minus I. Yeah, which is just 1. Yeah? So that means that this thing is just equal to 2 pi I. This was equal to 2 pi I. Yeah? Cool. So we're now going to break up the pieces of this. So we're going to parameterize the part of the curve which does the semicircle type thing. So let gamma of t be, it's going to be easier for me to think about this as in this way, or as I plus r times I e to the it, like this. So when t equals 0, I just go up by radius r, like this. So then the range of t I'm interested in is from... So I see what you're saying. It's just, for psychological reasons, it's just easier for me to put an I here, and I'll show you why. Because what I want to do is I want to think about the range of t that I'm interested in, right? So the range of t is, if t equals 0, then I'm here. Then to get this guy here, it's going to be something like taking t to be like pi over 2, right? But a little bit more than pi over 2. See what I mean? So I'm going to take t inside this interval, which I'm going to call theta 1 of r and theta 2 of r, where theta 1 of r is approximately minus pi over 2, right? It's this guy over here, yeah? But it's a little bit bigger, right? So I don't care to calculate how much bigger it is, because all I need to know is that the limit as r goes to infinity of this thing will be minus pi over 2. Yeah? And theta 2 of r will be approximately pi over 2, and the limit as capital R goes to infinity of is pi over 2. Yeah? So just by geometrical reasons, this should be reasonably clear to you guys. Are you happy with this? Yeah? Cool. So what have I got when I do this integral? So this thing, let's call this thing star. So star, actually it's so simple to write it, I might as well just rewrite it. So forget about that star stuff. So integral over gamma of r of 1 over w minus I dw has got two components. It's got the integral, so we're doing the anticlockwise parameterizations. We're going from a to b. So this is just this integral in this normal real sense of a of r to b of r of this thing. All right, dw, and this is just a standard real integral, right? And then the integral over the semicircle part. But now we're going to put in the parameterizations. The parameterization, we are going from theta 1 of r, theta 2 of r, right? And then we have this parameterization, so it's 1 over gamma of t minus I gamma prime of t. Right? And this is the guy that we're interested in. So this is the guy we need to evaluate. So let's call this guy star. So let's cut off some separate space like this. So then star is equal to the integral from gamma 2 of r, gamma 1 of r, oops. And what do we get when we put this in? So this I will cancel, so we'll have r. So we will have 1 over r I e to the I t, like this, yeah? And then what's gamma prime? Gamma prime, when we differentiate this, let's put it over here, gamma prime of t, we'll differentiate this, we'll have I times I, so it's going to be minus r e to the I times t, like this, yeah? So times minus r e to the I times t dt, yeah? And then we'll get some cancellations. So this is the integral from theta 2 of r, theta 1 of r, and maybe I should put this in brackets. So don't think it's minus. So we get cancellations like this. So this will cancel with this stuff right here, right? So all we'll have was minus I, which is just the same as I dt, right? So then this will just be I of theta 2 of r minus theta 1 of r, like this. Yeah, cool. And then that thing will tend to just pi as r tends to infinity, right? Because theta 2 of r is tending towards pi over 2, and theta 1 of r is tending to minus pi over 2. So this tends to I times pi as r tends to infinity. Again, I see this. Okay, so that's cool, right? So the integral around the semicircular part tends to this very convenient thing right here, which is just I times pi. Yeah? And this thing is tending towards the thing that we want, right? So as we take the limit as r tends to infinity of our actual integral, so the limit as capital R tends to infinity of the integral of this gamma of r, 1 over w minus I dw, right? That's the limit as r tends to infinity of this integral from a of r to b of r of this guy, 1 over w minus I dw, plus the limit of this guy, which we've just calculated is just I times pi. Yeah? And on this left-hand side, we know that for every single r, this is just 2 pi I. Yeah? So this implies that the limit, so we're using the fact we've calculated the residue and we know this, so the limit as r tends to infinity of the integral of a of r, b of r, 1 over w minus I dw, therefore is just pi times I, and then, so that's the same as saying that the integral over the whole real numbers is just this thing, equals pi times I, and that is our original claim. Yeah, that's our original claim. Cool. So with this claim, we have everything that's needed, right? So if you look back at the previous slides, whatever, we had that the integral inside had to converge to pi times I in order for us to have the identity that we wanted, just because continuity of f meant that this f times epsilon w as epsilon tends down to 0 tended closer and closer to just f of 0. So that is all we need for the proof of this particular formula. Okay, so yeah, it's a calculation, but it's a calculation we need, and now we know it's true. Okay, that will be it for today. We will use this to get the LP bound on the Hilbert transform on Wednesday. All right, thank you for your attention. Sorry for the overrun quite a bit, and yeah, send me your plan by the end of the week for your talks, and I'll see you all on Wednesday. Have a great day, people.